If you've watched our Mamba video, you know selective state space models match transformers at linear time. But Mamba-1 had real limits, a small state size due to hardware, complex custom kernels, and no clean theory connecting it to attention. Mamba-2, by Dao and Gu from May 2024, fixes all this. It's built on a beautiful theoretical framework called Structured State Space Duality, or SSD. The result is a model that's 2 to 8 times faster to train, supports a much larger state size, and has a simpler, hardware-friendly implementation. In this video we will recap Mamba-1 limits, dive into SSD theory, explore the SSM attention connection, understand the new block-decomposed algorithm, see the Mamba-2 architecture, and review the results. This assumes you've seen our Mamba SSM video and know attention and basic linear algebra. Alright, let's dive into Mamba-2. But first, a quick recap of Mamba-1 to set the stage. Mamba-1 introduced the concept of a selective state space model. Unlike traditional SSMs where the A, B, and C matrices are fixed, Mamba-1 made them dynamic. Specifically, the step size delta, the B matrix, and the C matrix all depend on the input token. This selection mechanism is what gives Mamba its power. To make this work efficiently on modern hardware, the authors developed a hardware-aware parallel scan. This algorithm used kernel fusion to overcome the memory bottleneck of a sequential scan. They trained models up to 2.8 billion parameters, demonstrating strong performance. The key benefits were linear time complexity for inference, a huge win over the quadratic cost of attention. In terms of quality, it was often comparable to transformers of a similar size. The core Mamba block combined a 1D causal convolution with this selective SSM, all wrapped in a gated MLP-style structure. This architecture proved highly effective. But Mamba-1 wasn't perfect, and it had several key limitations. First, the state dimension n was very small, typically just 16. Trying to increase n led to a significant slowdown. This was because the custom scan kernel, despite its cleverness, became memory-bound as n grew. The performance didn't scale with the increased computation. Second, the A matrix was structured as a per-channel scalar. This meant each of the D channels evolved independently, which limits the model's expressive power. There was no mixing of information across channels within the SSM recurrence itself. Third, the implementation relied on hand-tuned CUDA kernels. While fast, these are notoriously difficult to maintain and port to new hardware like TPUs. This created a high barrier to research and development. Finally, there was no clean theoretical link to attention. We suspected a connection, but it hadn't been formalized, leaving a gap in our understanding. This brings us to Mamba-2 and its core contributions, which address these limitations directly. First, and most importantly, it introduces a new theoretical framework called Structured State Space Duality, or SSD. This framework formally unifies SSMs with a variant of attention, explaining the deep connection between them. Second, Mamba-2 allows for a much larger state size. We can now use n values from 64 up to 256 with no slowdown, dramatically increasing the model's capacity. This is enabled by the third contribution, a new algorithm based entirely on matrix multiplications. This means it runs efficiently on standard hardware like tensor cores, removing the need for custom CUDA kernels. The practical result is our fourth contribution. Mamba-2 is 2 to 8 times faster to train than Mamba-1. Finally, this all leads to a much cleaner and simpler architecture featuring parallel projections, which we'll explore next. Alright, let's dive into the core theory behind Mamba-2, which the authors call Structured State Space Duality, or SSD. The big idea is a shift in perspective. We know state space models can be computed recurrently. But SSD reveals that any SSM with a diagonal A matrix can also be viewed as a structured matrix mixer. Think about it this way: instead of a sequential scan, the entire operation from input U to output Y can be represented by a single matrix multiplication. The output Y equals some matrix M times the input U. This M isn't just any dense matrix, it's a special kind of structured matrix called a semi-separable matrix. The specific structure of M is completely determined by the SSM parameters, a bar, B, and C. So, we have an equivalence. The SSM recurrence is the same operation as multiplying by this structured matrix. It's a new view on the exact same computation, and this duality is the key that unlocks major performance gains. So what exactly is a semi-separable matrix? Let's look at its structure. For a causal SSM, the matrix M must be lower triangular, meaning any entry M sub ij where I is less than j is 0. This enforces causality. For the lower triangular part, where I is greater than or equal to j, each entry has a very specific form. M sub ij equals C sub I times a product of a bar terms times B sub j. Specifically, it's the product of a bar from index k equals j plus 1, all the way up to I. You can see how the entries are factored into these three components. C sub I is the output projection, B sub j is the input projection, and the bar terms in the middle form a chain connecting them. This structure is the key. Storing the full dense matrix M would take O of n squared memory, which is prohibitive for long sequences. But because of this semi-separable structure, we only need to store the parameters a bar, B, and C, which only takes O of n memory. It's a highly compressed representation of a much larger operator. This duality gives us two completely equivalent ways to compute the same operation. View 1 is the familiar recurrent SSM scan. This is a sequential process that computes the output step by step. It's very memory efficient, running in O of n time and O of 1 extra memory, ignoring parameters. This is ideal for training on very long sequences or for autoregressive generation. View 2 is the new SSD perspective, materialize the M matrix and perform a direct matrix multiplication. This is computationally expensive, running in O of n squared time, but it's highly parallelizable. Modern GPUs with tensor cores are optimized for exactly this kind of dense matrix operation. So we have a trade-off. Mamba-2's key insight is not to choose one or the other, but to use both. It breaks a long sequence into smaller blocks. Within each block, it uses the fast matrix multiplication view. Between blocks, it uses the efficient recurrent view to pass the state. This hybrid approach gets the best of both worlds. So, how can Mamba-2 materialize this matrix M efficiently? The original Mamba had a state expansion factor, where a bar, B, and C were vectors, unique for each channel. This makes the matrix M different for every single channel. Forming that in parallel is complex. Mamba-2 introduces a crucial simplification: a bar is a scalar per head. It is not a vector. This means every channel within a given attention head shares the exact same a bar value. What does this do? It makes the structure of the semi-separable matrix M identical across all channels in the head. We are essentially applying the same linear operator to each channel's input sequence. This homogeneity is the key trick. It allows us to collapse the channel dimension and use highly optimized, batched matrix multiplication routines on the GPU. We trade per channel expressivity for a massive boost in hardware utilization. This is the core architectural change that enables SSD to be practical and fast. Let's connect the SSD formulation directly to attention. In standard attention, the output is a weighted sum of value vectors. The weights come from the attention matrix, which we compute as the softmax of QK transpose. So, each output token is a mix of all input value tokens, weighted by query key similarity. The structured state space duality, or SSD, presents a similar picture. Here, the output Y equals M times U. This is also a matrix mixer formulation. The matrix M is a large matrix that mixes the input sequence U. The key insight is that M in SSD plays the same conceptual role as the softmax of QK transpose matrix in attention. Both are sequence-to-sequence operators defined by a core mixing matrix. Understanding this parallel is the first step to seeing how Mamba-2 relates to the transformer world. So, what exactly is this M matrix in SSD? It plays the role of the attention matrix, and its components have direct analogs. The C vectors behave like queries. The B vectors behave like keys. The most interesting part is the structure between them. In SSD, the element M sub ij, which connects input j to output I, is formed by C sub I times a product of a scalars times B sub j. This product of A's is what implements the masking. It's not a standard binary causal mask where everything in the future is 0. Instead, it's a structured, weighted mask. This means Mamba-2 can be viewed as a particular masked attention mechanism. The mask itself is not just 0 or 1, it's a decaying value determined by the product of these learned scalars along the sequence path. This brings us to a critical difference in inductive bias between attention and SSD. Attention's softmax function computes fully content-dependent weights. The weight between two tokens is determined entirely by their query and key vectors, with no built-in notion of position. Any positional awareness must be added externally, usually with positional embeddings. SSD is different. The weights are structured by the product of a scalars. Since each A sub t is a value between 0 and 1, their product forms an exponential decay. This gives SSD a strong, built-in positional bias. Closer tokens naturally receive higher weights. So, while attention learns positional relationships from scratch, SSD has this decay bias baked into its architecture. This is a fundamental trade-off in their designs. This SSD perspective provides a powerful unification of modern sequence models. Many recent architectures, like linear attention, gated linear attention, RetNet, RWKV, and of course Mamba, can all be expressed in this matrix mixer framework where Y equals mu. They are all, in essence, forms of structured attention. Where they differ is in how they structure the matrix M. Each model makes a different choice, balancing computational complexity, parallelizability, and inductive biases like exponential decay. The SSD formulation makes this explicit. It provides a conceptual lens for sequence modeling. The game is no longer just about attention versus recurrence, it's about designing the most effective structured matrix M for your specific task and hardware constraints. Mamba-2's innovation is one powerful point in this vast design space. Okay, let's dive into the core algorithm of Mamba-2, the structured state space duality, or SSD. The key insight is a beautiful hardware-aware decomposition. Instead of processing a long sequence element by element, SSD splits the input sequence of length n into smaller, manageable blocks. Each block has a fixed length L, typically 64 or 1.8. Within each block, the computation is done with a dense matrix multiplication. Now you might think, wait, that's quadratic in the block length, O of L squared. And you're right. But this is exactly what modern GPUs are built for. These dense operations are incredibly friendly to tensor cores, making them blisteringly fast. Then, to connect the blocks, SSD uses a low-cost linear time scan. This scan efficiently passes the carried state from the end of one block to the beginning of the next. So you get the best of both worlds, highly optimized, parallel computation within blocks, and an efficient sequential scan between them. It's a hybrid that perfectly balances theoretical complexity with practical hardware performance. So, how does this work in practice? Let's break it down into 3 steps. First is the intra-block computation. For every block, we compute a partial output in parallel, completely independent of other blocks. This is the O of n times L squared part of the work, but again, it's all done with matrix multiplies that saturate the GPU. Step 2 is the interblock scan. This part is sequential. We take the final state from block 1 and use it to start computation for block 2, and so on. This is a very small, cheap recurrence, just passing a state vector from one block to the next. The final step is combination. We take the partial output from the intrablock step and add the contribution that comes from the state passed down by all previous blocks. This gives us the final, correct output for each element. the total work for the SSD layer is roughly O of n times L. This is subquadratic, but crucially, most of that work is in the tensor core-friendly matmuls. This brings us to the most important question: why is this so much faster? The magic lies in the hardware, specifically the tensor cores on NVIDIA GPUs. Mamba-1 scan was an element-wise recurrence. It was very memory-bound and couldn't be expressed as a large matrix multiplication. This means it couldn't use tensor cores, leaving a massive amount of the chip's potential on the table. The SSD algorithm, by design, maps the bulk of its computation to these dense O of L squared matmuls inside each block. This leverages tensor cores directly, giving you a 5 to 10 times flop advantage over general-purpose CUDA cores. This hardware-aware design is the direct cause of the 2 to 8 times speedup over the original Mamba. And there's a great bonus: this block-based approach is much simpler to implement. For many common use cases, you can write a high-performance version in pure PyTorch without needing any custom CUDA kernels, which is a huge win. Alright, let's dive into the Mamba-2 block. The biggest architectural shift from Mamba-1 is how we generate the state space parameters. In the original Mamba, the projections for B, C, and the time step delta were sequential. Mamba-2 completely parallelizes this. At the start of the block, we perform a single, large matrix multiplication on the input. This one operation computes all the needed quantities at once, the main projection of X, plus the projections for B, C, and delta. This is a massive simplification. The flow becomes crystal clear: one parallel projection, then the core SSD operation, which we covered earlier, and finally an output projection. This design heavily reuses matrix multiplication, which is exactly what modern GPUs are built to accelerate. It trades a more complex sequential path for a simple, parallel, and highly efficient computation graph. This change is fundamental to Mamba-2 performance. Next, Mamba-2 formally introduces a multi-head structure, much like we see in transformers. The model is divided into H-heads, where each head operates on its own smaller state of size, n. And this state size n is now much larger, often 64 or even up to 256, compared to 16 in the original Mamba. Why was this easy before? In Mamba-1, the A parameter was a vector different for each channel. This made sharing parameters across heads complicated. But in Mamba-2, as we saw, A is just a single scalar. This simple change makes multi-head design trivial. Heads can now easily share the same A parameter. They can also share parts of the input and output projection matrices. This opens up a huge design space for different sharing strategies, offering a better trade-off between model capacity and parameter count. So, what does the full Mamba-2 model look like? It's elegantly simple. We just stack these Mamba-2 blocks one after another, typically with normalization layers and residual connections, just like in a standard transformer. The structured state space, or SSD paper, provides a whole family of pre-trained models. They range in size from a small 130 million parameter model, all the way up to 7 billion parameters, with several sizes in between. The paper also publishes many different architectural configurations, exploring the trade-offs in the design space. To ensure a direct and fair comparison against the original Mamba, these models were trained on the exact same dataset, the pile, using the same data processing. This allows us to attribute performance gains directly to the new Mamba-2 architecture. All right, let's look at the results. How does Mamba-2 perform in practice? The biggest win is speed. On modern hardware, Mamba-2 training step time is significantly faster than Mamba-1. We're seeing a 2 to 8 times faster training speed across typical context lengths from 2K up to 16K. This speedup comes directly from the SSD algorithm's design, which avoids the memory-bound scan operation of the original Mamba. The plot here shows this clearly. You can see the training step time on the y-axis versus sequence length on the x-axis. The transformer's quadratic scaling is obvious. But notice the gap between Mamba-1 and Mamba-2. Mamba-2 is consistently faster. This isn't just about wall clock time. Activation memory is also a major bottleneck, and Mamba-2 makes huge strides here. Mamba-1 memory scaled linearly with sequence length and state size n. In Mamba-2, it's now logarithmic with n. This allows us to scale to much longer sequences and use a much larger state size, going from n equals 64 to 256 and beyond, which is crucial for model quality. But what about quality? Does the new SSD formulation hurt performance? The answer is no. At smaller model sizes, Mamba-2 quality, measured by perplexity, is on par with the original Mamba. However, thanks to the efficiency gains, we can scale up the state dimension n. And this is where Mamba-2 really shines. At larger scales, it consistently outperforms Mamba-1. This plot shows perplexity versus model size. Lower is better. You can see that our Mamba-2 7 billion parameter model is competitive with much larger models like Pythia 6, 9b, and it also matches the performance of a similarly sized Mamba-1 8b model. Furthermore, the Mamba-2 block is very flexible. We can create powerful hybrid models by interleaving Mamba-2 blocks with standard attention blocks. These hybrids capitalize on the strengths of both architecture's global context of attention and the linear time efficiency of Mamba-2. The results are excellent, achieving state-of-the-art perplexity for their parameter count. To recap Mamba-2, the SSD framework gives us 2 to 8 times speedups on modern GPUs. It achieves this with a larger state and a tensor core-friendly design. For all the details, check our paper on RZIV 2004-05. 2060 and the code on the statespaces/Mamba GitHub. Coming up next, we'll introduce Jamba, a hybrid Mamba attention MOE that hit 256K context production ready.